just hitting the record button there. Parker, how are you? Oh, I can't hear you for some reason. Maybe your mic's not working, Parker.
Good so far.
Okay, gotcha. All right. Jameel, how are you?
How you doing, sir?
Good. Hey, I saw you had a big game. I saw some pretty good pictures of you and Eric. Yeah, you guys were looking good all over social media. You know, there's at least 3 million people that follow Asbury's Twitter feed. So you guys were all over the news, Jameel.
Oh man, I love the support. I appreciate it.
Hey, Max, how are you?
Good. How are you doing?
I am doing okay. Doing okay. All right. James, how are you?
Good.
Right. I see Evan. What kind of hat is that? I can't make out the logo.
It's a Lakers hat.
Oh, it's a Lakers hat. Okay. Awesome. Awesome. Thank you.
Yeah.
That's cool. Nathan, how are you?
Doing good. Doing good.
Good. Good to see you. Let's see. Walker, how are you? I think you were in the news too recently, weren't you? I thought
Yeah, I
so.
was.
Yeah. Okay. It was good things, right? Nothing bad. All good. Zane, how are you?
I'm a little cold, but hanging in there. How are you?
Do they not turn the heat on in the dorms now, or what do they do?
Well, we got some heat, but it's just like an overall cold feeling today.
Yes, I agree completely. I agree. Let's see, Gabrielle, how are you? I can't see your smiling face.
I'm good. Sorry, my camera's acting up today.
Uh-oh. Okay. All right. Jesse, how are you?
I'm doing well.
All right. Oh, where'd you go? Oh, there you hopped around on my screen there. Okay. I see David. All right. There's Maddie. Yeah. Eric, I was just telling Jameel, you guys were all over social media with a nice win the other day. So congratulations.
Thank you. Appreciate it.
Yes, sir. There's Carter. Jesse. Trey, how are you?
Good. How are you?
There he is. I'm doing okay. I'm staying warm in my man cave. I've got my little sign up there that says this is my man cave. So
I love it.
yeah, I'm in my man cave. And then Khalil, are you down there leaning next to a palm tree, or what's going on in your world?
Hey, I'm driving right now. Can you hear me?
I can. Oh no, don't look and drive at the same time.
No, it's good. It's okay. I can do this, but I'm good. Florida's pretty nice right now. It's very warm. It's 70 degrees right now.
Okay. Well, let's not talk about that.
I'm sure you guys are jealous of that.
I am very jealous. Yeah, one of my buddies, he lives in Orlando, and he was giving me a lot of jazz past couple of days about it being like 83 and all this stuff. So, oh well. I keep volunteering for setting up a Florida campus for Asbury, but I can't get anybody to help fund that for me. So, all right. Well, it's good to see everyone. We're, being flexible in our high flex mode here. And so I appreciate you guys jumping on Zoom. Let me go ahead and share my screen. And then let me jump over to, all right, can you guys see my screen okay? All right, so we're going to be spending today talking about probability. And it's pretty cool. In this part of the class, well, and we've talked about it otherwise, that some of the best examples to help make the point are in gambling. So I'm not endorsing gambling by any means, but you'll see some examples as we roll through of, games of chance as being good examples of probability. Let me go ahead and make this a little bit bigger. So it pains me to say, but one of these days we've got to have an exam. So it seems like a pretty good time. So here's what it'll look like. So it'll be a take-home exam. Okay. It'll be open book, open notes, Google, YouTube, all of those are available. Just cannot have any other human real-time help. Okay. But basically, as I release it on Friday, and then you turn it in on Monday, you pretty much got 4 full days to be able to work on it. Okay. It'll be a combination of problems, very much like the ones that you've been doing in your labs. And then I'll have some short answer questions. Okay. So I'll release it on Friday morning. I'll put it on Discovery and I'll probably email it as well. And then you guys can email your answers back to me on Monday night. Okay. Any questions about that? All right. Got that out of the way. All right. So let's talk about this idea of probability. If probably most of you are familiar with a deck of cards, a standard deck of playing cards is made up of 52 cards in total. And if we were in this particular example, if we were to look at a well shuffled deck of cards, which contains 4 aces, right? And then the other 48 cards, then what we would want to know is what is the probability of drawing an ace if we, just kind of randomly select one card. And so how do we figure that out, right? So in this example, what would say is the probability of selecting an ace would be in the numerator, the number of aces, right? And then in the denominator, the number of all of the cards, okay? That would be the entire sample. So in that case, there are 4 aces, and we would divide 4 into 52, and we would say that the probability of selecting an ace would be 1/13. So pretty simple. That's about the simplest kind of probability question that we can think about. But we're going to obviously build on that. I'm trying to think of, I guess the one that's relatively AA movie-wise is Rain Man. Have you guys seen that movie, Rain Man? It was many years ago, but it had Tom Cruise and Dustin Hoffman. And so kind of an interesting little Kentucky fact. So some of that movie, if you've seen that, was filmed in Northern Kentucky. And there's a scene in the movie where Tom Cruise's character and Dustin Hoffman's character are in a restaurant in Northern Kentucky, and there are I think it's an accident and a bunch of toothpicks fall to the floor. And Rain Man, who they call Rain Man, which is Dustin Hoffman, is able to look at the toothpicks and then immediately know how many are on the floor. And, because Tom Cruise's character recognizes that, they go to Las Vegas, and because Rain Man has this incredible intellect to be able to count cards and keep track of many, many different things, then, they, at least in the movie, make a lot of money in Las Vegas. So all that to say, there are games of chance like blackjack or, poker or what have you, 5-card draw or whatever, that you kind of have to think about, okay, what's in my hand? What does the dealer have? What do other people have? And you have to kind of click through in your head. Here are the cards that I know are present. Here are cards that I don't know if they're present or not, but I'm pretty sure they're not. And then you're starting to do, if you can do this kind of work, you're starting to think about what's the probability of someone who has 3 3s and a pair of 2s, or I'm sorry, a pair of 3s and a pair of 2s, that they would draw a 3 or a 2 to have a full house if you were playing 5-card stud. So these are the kinds of calculations that you can use in a real world kind of setting. So, but again, I'm not saying, hey, go to Las Vegas and gamble. But that would be kind of a basic real world example of that. All right. Let's take another example, one that is not gambling, but it has to do with managing risk or managing probability. So in this kind of fictional example, before including coverage for certain types of dental problems. So you guys have all been to the dentist, and some of you have had cavities, some of you have never had a cavity. But this idea of insurance is, I am making a payment, let's say a monthly premium if you have dental insurance, in the event that I get a cavity, or I have to have a crown, or I have to have my tooth pulled, or what have you. And so that's kind of the nature of insurance. It's managing that kind of risk. So before, let's say, a dental insurance company considers coverage for some type of dental problems, they wish to determine the probability of occurrence of such problems. So those of you that want to be a statistician, it's the few, the proud. But if that's something you want to do, they go hire a statistician and pay them a lot of money. And they collect data for 10,000 adults in the appropriate age range and find that 100 people have experienced a particular dental problem during the past year. So the probability of occurrence, right, similar to our card example, is 100 divided by 10,000, or 0.01 or 1%. Okay. So let me pause. Any questions about that example so far? And I'm going to ask like a bonus question here. So let's see, Evan. I was looking for Evan here real quick. There he is. I don't see Evan, but I see that you're on. So Evan, let's kind of connect this probability idea with the idea of paying a premium. Okay. So if, let's say in this case, the probability for some weird reason initially was estimated at 0.01. and the premiums that someone would pay to a particular dental insurance, let's say, are $10 a month. And let's say they hire a new statistician, they take a new sample, and instead of it being 0.01, it actually is 0.05 or 5%. What do we think would happen to the premium that would need to be paid associated with having that dental insurance? Would it go up or go down?
It'd go up.
It would go up. Why would you say that? You're right.
Because if it's 5%, it's more likely that you'll have to pay, so they need to get more money out of it.
Yeah, that's exactly right. So if you know they're looking at a risk adjusted situation and they say, hey, well, guess what? We underestimated our likelihood of having to make a payout on this particular dental situation, and we underestimated it by 80% below what it really is. And therefore my chances are 5x what I thought they were, then I can't keep my premiums at $10 a month. I'm going to have to increase them. Now, it'd be kind of a marketing question, right? Do I automatically go from 10 to $50 a month? Or do I say, holy cow, I mean, if I do that, I might lose a bunch of customers because they'll be like, hey, I've been paying $10 a month for dental insurance for 10 years. And now you guys are bumping it up to 50. I'm not good with that. Right. So that's kind of this interesting interplay where probability meets, the idea of insurance. And those of you that have car insurance, which I'm guessing is most of you, if God forbid you've had an accident, and especially if your parents are helping you pay your car insurance and they find out you had an accident, they're probably not going to be happy. Why is that, Nicholas? Why would they be upset?
Because they'll be the ones having to deal with the financial consequences of it.
Yeah, well, the insurance premiums are going to go up, right? Mm-hmm. And so one little interesting factoid here. So I'll just pause. So those of you here, how many of, let me just ask the guys, how many of you guys have sisters? Okay, several of you. So I don't know if you know this or not, but can you guess whether the car insurance that you and or your parents pay for your insurance, guys, is it higher or lower or the same than your sister's insurance?
Higher.
It's higher. Why is it higher, Khalil?
It's higher because this is what I've heard. I don't know if it's true, but I think it's because of, I guess, guys' brains don't fully develop until 25. It's like the part of our brain that makes decisions doesn't fully develop. So we are, I guess, statistically stupider on the roads, and we are more likely to get in accidents. So our premiums will be higher.
Yeah, I'm not sure about the brain science, although I have heard that up until a certain age, both males and females, somewhere in the brain wiring, the cause and the consequence doesn't necessarily get connected till later. I don't know what that is, but you're right. Guys in general will have more accidents, young men more than young women. Although I still find that interesting. But that's probably another topic for another day. So yeah, I mean, that is, one way. If you wonder, well, how come I'm paying $100 a month for car insurance and my sister's only paying $70 a month for car insurance? It's because probabilistically young men get in more accidents than young women. So, right. So Let's kind of ground ourselves in this idea of probability. So we're going to use the symbol P for probability to designate the probability of any given event. And one thing is kind of, I think, pretty interesting is that for any particular event, the probability of that event happening would have to be between 0 and 1. Okay. And so that's where sometimes we say, well, many things in life are binary. It's either a 0 or 1. If we think about the digitization of our world over the last 30, 40 years, it's basically turning different decisions and events into a 0 or 1. Either it happened or it didn't happen, right? And so that's helpful for us to kind of conceptualize this idea of probability that for any particular event, it would be between 0 and 1. And then if there are many, many events, you're going to see that probability be somewhere between 0 and 1 as more and more of those events occur or don't occur. Okay, so we have the blob chart here. Okay, I'm not sure what this looks like. Maybe it's like a kidney bean or whatever it is. I guess you can decide whatever that looks like to you, the ink blot test. But here's an example of if we are looking at the probability of event A happening, what we would do is we would say, okay, let's say that, conceptually this square in the area of this, or excuse me, of this rectangle is 1. And so what we would say is the probability of A happening, which is this kind of blob here, the space occupied by A, is some percentage less than 100% of the entire rectangle, right? And so conceptually, what we would say is that A and not A are the inverse of one another, right? So for example, if the probability associated with the area A is 0.5, then what we would know by definition is the probability of A not happening would be 0.5 as well. Okay, so that's just really another way of thinking about this equation here at the bottom of this chart. So that's kind of one truism that we want to be rooted in. The second one is this idea of mutual exclusivity and non-mutually exclusive. And so, you might say, well, what is mutually exclusive? Well, it's important for us to recognize that this notion of mutual exclusivity is where two events cannot happen at the same time. Okay. So one happens or the other happens. Okay. And so if we're looking at this conceptual chart, what we would say is that in this actually looks like a square. In this square, we have event A, which is this left circle. We have event B, which is this right circle. And then the probability of A or B happening would be the probability of A plus the probability of B. So let me pause and see, can you guys think of any examples of events in your world that would be mutually exclusive?
If you have two sports teams playing against each other, one of them has to win the game.
Nice. Okay. Unless there's a tie that's allowed somehow. But are there, I guess, what are the sports where you can tie? soccer and hockey. Is there anything else?
The NFL you can tie.
Ah, is that right? I guess I'd forgotten
Yes.
about that. It used to be like sudden death forever. I thought it was until somebody won. But okay, yeah, yep. So yeah, I mean, let's say it's a sport where there are no ties. So right, in baseball, you play until somebody wins, right? You go into extra innings. What would be another example of mutually exclusive events? Let's see, where's Eric? Let's see, is Eric there? I might have, there you
Yeah, I'm
are.
right here.
There you are. Okay, so Eric, I'm going to ask a really silly question. So when you're shooting a free throw, can you make a half a free throw?
No.
No. You can either make one or you don't, right? So the making a free throw or not making a free throw, those are mutually exclusive. I can't like have a half a free throw, can I?
No, you can't.
No. That might be cool. You know, it might be interesting to go back in time and see all of those rim runners or whatever that went around and around and then decided the game, you know, if that was like a half, that could open up Pandora's box, couldn't it? So yeah, I mean, this idea of mutual exclusivity is something that's going to serve us well when we start to think about if two events are mutually exclusive, what are the implications for the probabilities associated with those events? Okay. Here's an example of non-mutually exclusive events. So we have probability, or we have event A here, and we have event B here, and then we see that there is some overlap, right? And so if we wanted to know what is the probability of A or B, then what is the math behind that? So we're going to have to take the probability of A plus the probability of B, and then I'm going to have to minus out this intersection right here. So what would be an example of non-mutually exclusive events? Can you guys think of a non-mutually exclusive event? What about what about okay, I have to be a little careful here. So gender has been historically thought of as mutually exclusive, male and female. But then what we can do is we could say gender and your major in college, those are not mutually exclusive, right? Assuming that you're not undeclared forever at Asbury. A non-mutually exclusive event would be being a male and majoring in finance, or being a female and majoring in accounting, right? So those are two events, but there is an intersection where gender and major would overlap. Can anybody else think of another example of that? Nobody?
I was thinking, like if you and a friend go out to eat and you're trying to decide where to go and you both want to go somewhere else, then you've got the chance that you go to one or the other, and then you have the chance that you go to both, maybe.
Ooh, that's pretty cool, right? So that might be interesting. So maybe you, Zane, you want to go to this Mexican restaurant and they've got like these amazing fish tacos, but your friend wants to go to a steakhouse And so maybe they don't have great desserts at the Mexican restaurant, although fried ice cream is really, really good. But the steakhouse, they have, let's say, cheesecake, cherry cheesecake. And so, yeah, maybe you guys decide that I'm gonna kind of split my eating event. So I'm going to eat my main meal at one place, and then I'm going to eat my dessert at another place. That's a little bit of a stretch, isn't it, though? Trying to think of another example. The way that I like to think about it is when you're looking at categories of people and what they do. So you have demographic characteristics around gender and age and income, education level, and so on. And then you can have those demographic characteristics intersect with behavior, let's say. So you've got demographic characteristics, age, income, gender, and then behavior is went to college, didn't go to college, live in Florida, live in Kentucky, been to Disney World, not been to Disney, whatever it is. When you look at the intersection of those demographic characteristics and different behaviors, then we have sort of like a matrix, and we look at the intersection of what is in the row and what is in the column. And that would be an example of non-mutually exclusive events. Okay. All right. Let's see. Come on, PowerPoint. He's stuck. Oh, there we go. I think he was asleep. Okay. So now let's go back to some of the theory around what some people call the classic definition of probability. So let's say that we have two dice. I never say that right. Sorry. We have two dice, and if they are normal dice, they have 6 sides, 1 through 6, 6 sides numbering 1 through 6. And so my entire sample frame, if I'm rolling 2 dice together, is 36, right? And so this little table helps us understand the frequency. So rolling 2, that would be a 1 and a 1. I can only have that happen one way, right? Rolling a 3, that can happen 2 ways. So it could be a 2 and a 1 or a 1 and a 2, right? Rolling a 4 can be a 2 and a 2, a 3 and a 1, and a 1 and a 3. And so you can kind of see how that works out. So our entire sample frame is 36, okay? 36 different potential outcomes. And so we might ask ourselves, what is the probability of rolling a combined 3, right? And so we look at our table and we say, okay, there are 2 different ways that I can roll a 3 when I'm rolling 2 fair dice, and it's a random roll. 2 divided by 36 would be the probability. And so that's 1/18. So what is that? That's like, I don't know, 5 point something percent. So that would be a way for us to think about probability as it relates to rolling dice. Here's another kind of marketing application. So suppose you've got 2 customers and they try a new product. So, having worked in research for almost 30 years, I've worked with lots of different customers, and, worked with different brand managers. We were trying to figure out, okay, we've got a new product that no one's seen before. We've got 2 customers, and we're going to have both of them interact with this product. And there are 4 outcomes. So let's say we're trying to figure out, hey, do we launch this product or not? So we've got a sample of 2, which is very risky, but we've got a sample of 2. What are the outcomes? They could both like the new product. They could both dislike the new product, or one could like, one dislike, and the other, and then the first dislike and the second like. And so if we're asking the question, what's the probability out of these 2 people that at least one dislikes the product, then it would be 3 out of 4, right? So we're going to count this one, 4th, we're going to count the 3rd, we're going to count the 2nd, okay? So this is obviously a hyper simplified example, but you can imagine if you're a brand manager at Procter & Gamble or at McDonald's or Yum Brands or what have you, this kind of probability exercise is going to have some financial implications, right? If you're going to launch a new cheeseburger, let's say, you want to know how many people out of 1,000 that try this new cheeseburger are going to like it or not. And if we have a random sample and we have the proportion of 3 out of 4 people out of 1,000 or 750 don't like the cheeseburger, at least of one of the 2. So let's say we got 500 pairs, right? So then you might say, whoa, okay, if 3/4 of those outcomes, someone doesn't like it, I might want to say, you know what, let's put this on pause and let's come back to it later and see, is there something we need to do to tweak the product so that instead of the probability of dislikes is 3/4, maybe it goes to 1/4. Well, that maybe I can live with those odds, where 75% chance people are going to like the new product, and there's only a 1 in 4 chance, 25%, that people are not going to like the product. Another way that we can think about this idea of probability is over time. And so we've looked at this example before of relative frequency. So let's say we've got this fictitious computer repair. I need to get like a better example for next semester. But if let's say we are looking at relative frequencies as probabilities, and we're trying to understand what's the probability a computer is repaired in 10 days, then what I'm going to do is I'm going to look at each one of the frequencies of repairs by day, and then I'm going to sum all of these relative frequencies, right? And so what I would say is that the probability of repairing a given computer in 10 days, that's happened in total 19 times. And so the cumulative frequency, the relative frequency is 0.076. The cumulative frequency is 21.2. So again, this kind of analysis is helpful if you are working in a situation where you have to give a customer an estimated wait time, an estimated time before it's likely that your product or service is going to arrive. You probably all ordered stuff on Amazon or on eBay or whatever, and they usually give you kind of a shipping estimate, right? And so they've got a bunch of data that would say, if I've got a product that is in Spokane, Washington, and it's being shipped to Wilmore, Kentucky, I can look at all the other shipments that have been made through Amazon, and I can give you with some degree of certainty, that product should get from Spokane to Wilmore, or let's say Lexington, within a certain number of days, because I've got a bunch of data around different carriers, FedEx, UPS, and I can look at that and say, make a statement when someone hits checking out of their cart, and say, it's going to be there probably within 5 to 7 days. Okay. And so that's kind of what would be a real world application of this relative frequency. All right. So here are some kind of theorems or truisms around probability. So let's say that for a given experiment, there are n number of outcomes in a sample space. So you might be saying, well, what's a sample space? So one way to think about a sample space would be like this square or this rectangle with this blob inside and outside. Okay. So let's say that there are n outcomes in a given sample space. So observation 1, observation 2, all the way to observation n, where the the ith observation represents the ith outcome in the sample space. So therefore, the probability of the ith outcome occurring would be the probability associated with the outcome of the associated with the ith outcome. Okay. So, whoa, gosh, you can't see that. Do better on that. So if we look back at our theorem, we would say the probability associated with any outcome must be between 0 and 1. And then the probability of the ith outcome would be between 0 and 1, right? We established that a little bit earlier. And then finally, the sum of all probabilities over all possible outcomes must be equal to 1. So if we go back to this example here, the probability of A happening plus the probability of not A happening, these are mutually exclusive events. If I add these up, then I always will get 1. So every single one of the separate outcomes within a sampling frame all must add up to 1 when I look at each one of their individual or discrete probabilities. Okay. So back here, what we're saying is the probability given a sample space, observation 1 all the way to the ith observation, is probability of the first observation plus the second all the way to the nth will all equal 1. Okay. So that's one of our truisms for us to kind of think about. The PowerPoint gremlins got me. All right. So looked at that. Whoops. There we go. Sorry about that. So an event is a collection of one or more outcomes from a sample space. So if we think about, again, we're just kind of establishing these truisms or these rules. The probability of any event is the sum of the probabilities of the outcomes that comprise that event. So if we go back to our example of the 2 dice, the probability of rolling a 3 can happen 2 different ways, right? And if we look at all of those different outcomes, we would see that there's a total of 36, which becomes our denominator. And the numerator is looking at each one of those discrete events and the probability associated with each one of those discrete events in the numerator, adding all of those up and divided by the denominator. in every case, we will get one, right? That's kind of what we're saying in terms of a truism here. So we'll go back to our dice, and we're going to consider rolling a 7 or rolling an 11. So what we can see is there are 6 different ways if we have 2 fair dice to get a 7, okay? And then there are 2 ways to get an 11, okay? So again, not endorsing gambling, but if you've ever played craps or you've watched like a James Bond movie and they're all hoping for a 7. So there are, if you need to roll a 7 in craps, then there are 6 different ways you can get there, right? So a 6 and a 1, and 1 and 6, a 3 and a 4, 4 and a 3, and then 5 and a 2, and a 2 and a 5, right? So let's say that we're going to consider the events rolling a 7 or an 11. Okay. Can I roll a 7 and an 11 at the same time? Can I do that, Zane?
Nope.
I don't think you can do that. If you can, if you find someone that knows how to do that, please let me know. Okay. Might be a magician, who knows? So we're going to assume that those are mutually exclusive events. So we just listed how do I get a 7? There are 6 different ways. We just talked about what are the different ways I can get an 11, 6 and 5, 5 and 6. So I've got 6 different ways and 2 different ways, which corresponds to the 6 and the 2. So now what we're saying is, what is the probability of rolling a 7 or an 11? So I'm going to take the 6 different ways associated with rolling a 7, and I'm going to take the 2 different ways associated with rolling an 11, and I'm going to add those up, right? So remember from our rule around fractions, I've got to have a common denominator, which I do because the entire sample space is 36. So I'm going to take 6 divided by 36 associated with rolling a 7, and 2 divided by 36, which is associated with rolling an 11. And I'm going to add those together. And so what I have is 8 divided by 36. So that's my probability associated with rolling either in a 7 or an 11. Both of those events are mutually exclusive. Okay. Any questions so far? James, how are we doing? Are we tracking so far?
Yeah.
Okay, is this like easy? You learned this 10 years ago, or no, this is pretty good review, or what would you say?
It's a pretty good review, I think.
Yeah, it's probably not like you're spending every day thinking about this, so it's good to kind of dust that off, isn't it? Okay, all right. Yeah, so we will keep forging ahead. We're looking back at another example of our probability of our event of repair times. And so what we would say, if I can get my PowerPoint to work here, is that what is the probability associated with getting a computer repaired in 7 days or less? So I'm going to look at the probability associated with the first event the first outcome all the way to the 7th. And I'm going to add these up, right? So there's my first, second, third, fourth, fifth, sixth, 7th. Oh, day 0. Okay, so skip that. So I'm going to add all of these up from 0, 0, 0 all the way to 0.2. And so what does that tell me? Oops. Maybe I ought to get out of it. Okay, so right. So I'm looking at, I'm going to add up the 0, 0, 0, 0. There's my 4 zeros. Then I've got a 0, 0, 4, 0, 0, 8, and 0.02. I'm going to add all of those up so that what I can do, what I can do is I can make a statement to a potential customer and say, what is that, 0.028 rats? I thought I had, sorry guys. I'm gonna have to like add this up here real quick. I thought I had that. So I'm gonna add up, whoa, don't do that. All right, so I'm gonna add 0.04004, sorry, plus 0.008 plus 0.02 plus. So my probability associated with having a computer repaired in 7 days is not great. It's 3.2%, so not super great. Okay. Probably want to find a new computer repair place. So that's this idea of looking at an entire sample space and then looking at the various outcomes associated with that event in the sample space. So now let's move to this idea of the complement of an event. Okay. So remember when we said, if I have a probability event A, and then I have a probability of event non-A, so is the blob and then everything outside of the blob. If I take both of those things and add them together, I get 1. But in that same example, the complement of probability A is the probability of not A. So what does that mean? So if I want to understand what is the probability of an event not happening, then I'm going to take 1 and I'm going to subtract the probability of an event happening. Okay. So let's take our example of our event is rolling a 7 or 11. Remember we said that is 8 divided by 36. Well, what is the complement of that? So the complement would be, I'm going to take out the 7 and the 11, and then I'm going to add up this, all of the probabilities associated with rolling 2, 3, 4, 5, 6, 8, 9, right? I've skipped the 7, I skipped the 11, I go to 12. And so using our rule 2, I could add all of these up and divide by 36, but that's kind of a pain. A quicker way to do it would be to take the probability of the complement, which is 1 minus rolling the probability associated with rolling a 7 or 11, which would be, okay, so help me, James, what's my fraction here when I've got this 1? Because it'd be hard for me to take 1 and then subtract 8/36.
It's 36 over 36.
Okay, so I got to take 36 over 36, and then in numerator, I take 36 divided by 8, and then that leaves me with 28 in the numerator and then 36 in the denominator, right? Man, good job. We need to write a thank you note to one of your prior math teachers, don't we? Okay. Do you remember who your math teacher was that taught you this?
No, I don't.
Yeah, I don't either. She's probably not alive. God love her. I'm old. All right. So we talked about the complement. Okay. So now let's talk about the union. So here we're looking at 2 events that are not mutually exclusive. And what is the probability of 2 things happening at the same time? Okay. So if there are 2 events, A and B, the probability that there is some outcome in either A or B, the union of A or B is denoted as probability of A or B, right? The 2 events are mutually exclusive if they have no outcomes in common, right? So in our case of rolling a 7 or 11, they have no outcomes in common, and therefore, by definition, they're mutually exclusive. If, however, events A and B are mutually exclusive, then what we would say is the probability of A or B happening would be the probability of A plus the probability of B. Okay. So, one of my favorite things in this life are Venn diagrams. So James, can you kind of rally around the coolness of Venn diagrams? I mean, it's cool, right? So what would be, James, help me think about what would be an application here. So for you, James, well, let's take you out of the equation. So, because I don't want to put you on the spot now. So let's take me, the 18-year-old version of me. So my event A is I don't take a shower for a week. Okay. And then my probability for event B is going on a date with the prettiest girl in my college. Okay. I'm pretty sure that if I don't take a shower for a week, my odds of going out on a date with the prettiest girl are probably going to be non-existent. Is that a fair statement, James?
Yes.
I mean, that, at least in my head, that kind of makes sense to me. And so we can take these Venn diagrams and we can start to use them to help at least assess some kind of probability. So again, we can look at what's the probability of mutually exclusive events happening. So we already established the event of a 7 or 11 is 8 divided by 36. Let's say that the probability of B, which is a 2, a 3, or a 12, is 4 divided by 36. So we can see that there's my 2, that's a 1. Then I've got my 3, which is a 2. 1 plus 2 is 3. And then 12, there's a 1. So 1 plus 2 is 3, plus 1 is 4. Okay, so then what I would say is, what is the probability of the union of these two events, rolling an event A or an event B? The union of those two events is the probability of A, 8 over 36, plus the probability of B, 4 over 36, or 12, because I'm adding the numerators, right? 8 plus 4 is 12 divided by 36, or 1/3. Okay. All right. So this gets a little bit trickier when we're looking at non-mutually exclusive events. So let's say we have two events, A and B, and we're looking at the intersection because they're not mutually exclusive. That means that those the Venn diagram, those two circles in the Venn diagrams are going to overlap. Okay, so in that situation, if two events A and B are not mutually exclusive, then the probability of A happening or B happening, remember we have to take the probability of A and B just as if they were mutually exclusive, but then I got to minus out that area where those two events overlap, right? So in this case, if I'm trying to figure out what is the probability of A or B, I'm going to take the probability of A, which is this blue circle, and the probability of B, which is this red circle, but then I've got to subtract out this middle area, this middle section, which is the intersection here, the probability associated with A and B. Okay. So I gotta minus that out. So back to our dice example. So we've got our event A, we already know that's 4 out of 36. And then let's say, oh, okay, our event B is a little bit different. That is rolling an even number. Okay. So I already kind of got my A, right? I know what that is, 4 divided by 36. But then I got to go back and I see, okay, rolling an even number. So that there's an overlap there, right? You can see the red and the blue squares. And then there's an overlap here, which is rolling a 12, right? Because, and wait a second. Sorry, rolling a 4, rolling a 6. So what I've got to do, right? So my red are all of these even numbers, and then my blue are rolling a 3, excuse me, a 2, 3, or 12. But I do have these two overlap situations, the 12 and the 2. And so I've got to minus those out, right? So the probability of A or B is the probability of A, which is 4 over 36 plus 18 over 36, rolling an even number. But then I've got to subtract these two events where they overlap at 2 and at 12, right? So the right answer is 4 over 36 plus 18 over 36, which would be 22 over 36. But then I'm going to subtract the 2, the overlap, which would give me 20 over 36. So any questions about that? Who knew it would be this much fun to hang out with dice? I mean, this is like a new exciting thing for us, isn't it? So I was going to show you these videos, but I think that we kind of beat the dead horse while it's still down here. So any questions about probabilities and Venn diagrams? Anything? David, can you think of anything, or you think we covered it pretty well?
I think we got it.
I think we got it. I mean, I think that horse is down. We are kicking it. It's really not doing well because we've been kicking it so hard. All right. So so just kind of, you know, as we were saying at the top, so Thursday will be a lab, so I'll send those out. I'm guessing that we will not be on campus, or we will not have in-seat class on Thursday, at least based upon the forecast that is out there right now. And so what I'll do is I'll post the lab in Discovery, and then you guys can work on that, and then I'll release the midterm exam on Friday morning. So any questions about anything at all?
I have a quick one just
Yes,
about the test. With, I guess, do you mind posting your slides?
I will, yeah, and they're up there, and but I haven't posted the ones that we just went over, so I will do that. I'm also recording this, so I'll post this recording as well.
Awesome, thank you so much.
Makes sense? All right. Well, I will see you guys at least briefly for sure on Thursday, either in person or virtually. Okay. Have a great rest of your day. Thanks.
Hi, Professor.
All right. See you later. Drive safe.